In this video, we'll talk about how to train a neural network to play tic-tac-toe like this. It's kind of a recap of what we covered in the past few videos. We'll be using the minimax algorithm to train the network. And before we dive in, we'll take a quick review on what a multilayer perceptron or MLP is and how the minimax algorithm works. This link goes over the basic ideas behind the multilayer perceptron, MLP. We discussed before that a multilayer perceptron is a supervised learning process in artificial intelligence. So an MLP consists of an input layer, one or more hidden layers, and an output layer. So we feed an MLP an input pattern x, x1, x2 to xn, as shown here. So each of this is a neuron, and then we calculate from this input pattern and the ways the input to a neuron of the hidden layer. And then eventually we generate an output pattern, say y, y1 to yk. So this output pattern is compared with our targeted output. We calculate the difference, the error between this calculated output and target output, so we get error, and we fit this back to adjust the weights. And then we calculate all the input values and output values. We iterate this many times so that the targeted output and the predicted output will converge to each other. And so this shows the details of the calculations. We use a sigma function to calculate the final input to a neuron of the input layer or the hidden layer. So it is calculated by these formulas, basically the sum over the weights and the input values, and then fit this value into a activation function, like a sigma function. And so then we have the back propagation process. So basically to calculate the error and then feed it back to adjust the weights. So that's called back propagation. So we discussed is implementation in C, C++. And we used exclusive OR as example, and also a binary full adder as an example. So we basically will use the same program to train tic-tac-toe, but of course we will change the constants here. This link goes over the basic ideas behind the minimax procedure. In an adversarial game like chess, a player may look ahead several moves in advance. The sequences of moves may be represented by a game tree. The root represents the initial conditions. Branches from the root represent legal moves the first player could make. At the next level, branches represent legal moves of the second player, and so on. In practice, for any interesting game we played by the computer, we need some kind of evaluation function to examine the current situation and return a score assessing its benefits. To be definite, we assume larger values to represent favorable situations for the first player, and thus smaller or more negative values reflect favorable conditions for the second player. In a tic-tac-toe game, if the first player wins, then it gains positive 1 point. If it lost, it gets negative 1 point. If it draws, it's 0 point. So the strategy is that the first player selects the move that maximizes the score. The second player selects the move that minimizes the score. When looking ahead in the game tree, we only apply the evaluation function at the leaf nodes. There is position beyond which we will not search further. By working up from the bottom, we can assign values to all nodes. Since we alternately take minima and maxima, this procedure is called minimax procedure. So this is a minimax game tree for a tic-tac-toe game. So we start with the X move, and so if X moves here, then O can move here, and then we do the evaluation at the leaf. Okay, so this is the X wins, so get positive 1 point. This is draw 0, and this is 0. Okay. And for this, it lost, so it's negative 1 point. Okay. So at the root, so is the max, and next level is min, max. Okay, and so the maximum of 1 is 1, 0 is 0, 0 is 0, and the maximum of 1 is 1. Okay, this is the leaf. So this is the minimal level. So the minimum of negative 1 and positive negative 1. Okay. And the minimum of negative 1 and 0 is negative 1. And the minimum of 0 and plus 1 is 0. Okay. And at this level, it takes the maximum. So the maximum of negative 1, 0 is 0. Okay. So that means in the game, X will will take this route. Okay. So that means we'll put an X here. Okay. And then the O, okay, will minimize the score. That means we will take this route. Okay. That means you will put an O here. Okay. And X, okay, we put X here, so there's a joke. Okay. There's how the minimax algorithm works. Okay. Now this is the program that implements the minimax procedure for the tic-tac-toe game. We discussed this in a previous video. We will use this same program to train our MLP to play the tic-tac-toe game. Now let's see how we can train a multilayer perceptron, MLP, to play tic-tac-toe. There are many ways to do it. Here's one design. In this design, we have 9 input neurons and 9 output neurons. Each input neuron can have 3 values, 1, -1, or 0, okay, corresponding to whether we mark the circle or square by X or O or empty. Now in this example, say A1, okay, in this neuron, it is marked by X, so this 1, okay, and then OO, so -1, -1, and then empty, so 0, okay, and then marked by XX, so there's 1, 1, empty, empty, so it is 0, 0, and then O, so -1. Okay. And for the output, say we would like to mark this square by X. Okay. So we put an X here. So that means here the output should have a value close to 1. Others should have values close to 0. So this position is 1, 2, 3, 4. Okay. 1, 2, 3, 4. So this is our targeted output neuron. So it has a value close to 1. Others have values close to 0. Okay. So this is one way to do it. And in this case, each input neuron can have 3 different values, -1, 0, or 1. It is not binary. Okay, so we have to use the softmax function as our activation function. Okay. And since we want to reuse the programs we have written to train the binary full adder or the exclusive OR gate, we want to keep the inputs and outputs to be binary. Okay. So we'll use a design like this. So here, okay, we have 19 inputs to be compatible with what we have written. X0 is our bias. It is always equal to 1. And X1 to X9 for X, and X10 to X18 for O. Okay. And we have 9 outputs, okay, Y0 to Y8. Okay. So as shown here, so X0 is always 1. It is the bias. Okay. And then X1 to X9 is for player X. X10 to X18 is for player O. Okay. The outputs are Y0 to Y8. Okay. For example, say in this board, the inputs and outputs will be like this, because this is marked by X, so this is 1. This is X0, which is always 1, which is the bias. Okay. And then we have OOs, that's represented by these X values. So that means X11, X12, okay, we'll get 1. Okay. And also in this position, 1, 2, 3, 4, 5. Okay, we get X, so that means 1, 2, 3, 4, 5. So we get 1 here. Okay, and others are 0. Okay. And for the output, now we would like to put an X here. Okay, so this is position 8. Okay, so that means the target output will be like this. Okay, there are 1 here. So these are the inputs and outputs for this board. To implement this MLP, we can essentially use the same code mentioned in the above link, this link. This is the header file of the MLP class. So N1 is the number of inputs plus the bias. So it is equal to 19, okay, from X0 to X18. X0 is the bias. Okay. And K is the number of outputs. It is 9. Okay. The 9 outputs here from Y0 to Y8. Okay. And M1 is the number of hidden nodes plus the bias. Okay. The number of hidden nodes here, it is found empirically. We have to define a database data structure. Okay. Here, the struct is to record or hold the inputs and targeted output data or desired outputs, the labels here. Okay. The vector array double N1 means we have a vector of arrays, and each array has N1 values. So that means this vector holds a set of X arrays, X values. Okay? So X0 to X19 is stored in one array. Okay? And then this whole array is pushed into a vector. Okay? And we call this whole thing inputs. So basically this is a 2D array, okay, like this. And this is for the targeted outputs, labels, we call labels, okay. And so we'll use the values we got here to train the MLP. So all these are the same as before, except that we have added two more member functions. Save ways is to save the ways, these ways, into a file, okay, specified by the f name. And read ways is to read the ways from this file into these 2D arrays. Now we have copied we'll copy this into this directory. So this is MLP.h. Okay. So the one that we just mentioned. And this is the MLP.cpp. Okay, so we discussed this in the link mentioned. And this is the training function. We have to pass in the sample data contained in the database. Okay. And we use that to train the trained MLP. Okay. So we get the data from the inputs, okay, and labels contains the targeted output. Okay. So that's the train, and this is save ways, and read the ways. Okay. Now we can compile this. So there's no error. Okay. Okay, so you can see that this object file is created. We have also copied the minimax programs to this directory, minimax.cpp, minimax.h. Okay, this is the same program that we mentioned in the above link, this link. Now we can take a look at these files. This is the header and the program. Okay, so this is the minimax class. Okay, we call it minimax T because it is for playing tic-tac-toe. Okay. So it's a constructor. We set board, print board is winning to tell if the player is winning. Empty cell to tell if the board still has empty space. Evaluation is the evaluation function. Now this is the minimax function. Okay. So the one segment is to maximize the score, and the other segment is to minimize the score. And again, this function is called recursive. Go deeper and deeper. And we can compile this. So you can see that there's no error. And we get this object file minimax.o. Now, the challenging part of this project is to build a database for training the MLP. So here we will use a technique called depth first search, or DFS, to collect the inputs of the tic-tac-toe board. The idea of this technique is that when we visit a graph or a tree, we try to go as deep as possible. When we could not go further, then we backtrack to the previous position and find another way and go as deep as possible. Okay. So basically this is what's happening in recursion programming. Okay. So the recursion function will call itself and again until the exit condition is met. Okay. Now, for example, here if we use DFS to traverse this tree, so we start with the root, so we go to 2. So instead of visiting 7, so we'll go further, we go to 3, and then to 4. Now we cannot go further, so we backtrack to 3, and then visit 5. Okay, and so all these are done. Then we backtrack to 2, then visit 6, and then backtrack to 1. Okay, and then 7, and so on. Okay. Now here's another example. So we start from 1, so we go as deep as possible. So we go to 3, 4, 7. Okay, backtrack to 4, okay, and then 3, and visit 5, and go back, and for 3, so we now go deeper instead of returning, because we haven't visited this 6, so we go to 6, and then 9, 10, and then go back, okay, all the way back to 1, okay, and then visit 2. Okay. So there's the DFS technique. This is the algorithm for building a database to train the MLP. Okay. So the argument board here is a tic-tac-toe board, 9 squares. Okay. And the player, current player could be X or O. Okay. The database DB here is the database we mentioned here. Okay. Yes, the data structure is like this. Okay. Vector of n1 arrays, and the other one is a vector of k value, a vector of arrays of k values. So if a player has won, or if it is a draw, then it's done. So we return. So this is the exit situation. Otherwise, we need to continue to play. So if the current player is AI, suppose it is X, okay, then we get a move from the minimax function. Okay, so if it is a legitimate move, we was declare the input array n1 values, okay, and then change the board to input values. So this function board to inputs will convert the board like this into input values like this. Okay. And labels is targeted output. Only this move, okay, return from minimax, will have a value 1. Okay, only this location has 1. Others will be 0. Okay, as we mentioned in this example, say the targeted output will be this guy. So that means I have 1 here. Others are 0. Okay. Then we have to scan other empty squares. Okay. So if the board is board I is empty, then we set it to be the current player, say X. Okay. And we call the function recursively, build the database, use the same board. The other player means say O, for example, okay, and pass in the DB to continue to construct the database. Okay. And now when the next case will be O, then you won't get into this routine. Okay, so get back to here immediately, and we just put the O to be in an empty space, and we call this again. Okay, and the other player now is X. Okay, so that means we go back in to find a move. Okay, so, and then we cannot go further. We get a situation, then we backtrack, restore the board. Okay, just like what we explained here. Okay. So in this case, we'll scan the board and we'll collect most of the input patterns. This is the C++ implementation of a program that trains an MLP to play tic-tac-toe. It's very basic. You can always improve upon it. Now this function add database is to add the inputs array and the outputs array, we call it targets here, to the database DB. Okay. Now the database has this structure. Okay. So it has an array, a vector of array of n1 tuples. Okay, that's the inputs, and also a vector of an array of k tuples. Okay, we call labels. Okay. And the labels corresponds to the targets here. Okay, so we create an array of n1 tuples. We call it temp_i, and an array of k tuples, temp_t. Okay, so we copy these input values to trade 19, okay, to temp_i, okay, and push back. That means insert into this vector DB the inputs. Okay, this is a vector, the inputs vector. We'll push back, okay, push at the back. And we do the same thing for the targets. The the desired outputs. Okay. We put that into this temp T, okay. And then we push it into the db's labels vector. Okay. So that means we save all the inputs and outputs, targeted outputs. And this function board to inputs is to change the board configurations input into the input pattern. So basically, if it is an X, we put that in the upper half of the inputs array. If it is an O, we put that into the lower half of the inputs array. Okay, so basically the implementation of this, okay, as discussed earlier. And we discussed the build database earlier. Okay. So we pass in the Tic-Tac-Toe class, okay, and the current pair and the DP, and we do this recursively. Okay. So here, if the current pair is X, then the next pair will be O. Okay. Or if the current pair is O, the next pair will be X. Okay. And then we call this recursively as discussed. And after that, we store the board after it returns, it exits. Okay. Or we are doing the backtracking. Out to move is to convert the output to a move. So basically, we find the maximum of the output. Say the output should have the maximum value. Okay, others should have values close to 0. Okay, the output neuron. And so we converted output to a particular move, okay, from this output array. Okay. And so this is the main. We create a database DB, okay, and the AI is X, the opponent is O, and then the returns to play the game. We use the minimax to do the training. So we create a minimax class called Tic, okay, and then build a database using this minimax class Tic, okay, as discussed. Now, after building this database, then we can use it to do the training, okay, as explained, because we have all the inputs and corresponding targeted outputs. And we'll train it for 30 times, iterations. So we call the function train, the DP, okay, iterations. And after that, we save the weights into the text file, tickweights.txt. Okay. And then we set the block after training. So this begins to play as we discussed in a previous video. And now we define two variables, move and neural move. The neural move is the move we obtained from the MLP, the multilayer perceptron. And this move is from the minimax algorithm. So we try to compare them. Okay. So so this move from the minimax, okay, and so we on the other hand, we obtain the inputs, okay, from the input pattern, okay, int, okay, the board to inputs. So the inputs from the board, okay, we pass in this. Remember, we need something to convert the board to this input pattern. So we convert to the input pattern, and then using this input pattern, okay, we get the output values, okay, the outs, okay, and so the move, okay, is obtained from out to move, okay, out to move this function, okay. And so we call this neural move, and we put AI to be the square specified by this neural move, and we compare this. Okay, we also print out the move obtained by minimax and see if they are consistent. Okay, so but we basically use these to the MLP, okay, trained MLP to play the game. Okay, and then is the user's turn. Okay, we continue to play this, okay, until there's a result. Okay, then we break out. Okay, so now let's copy and compile this program and see how it works. We copy this and paste it into this file, take mlp.cpp. So this is the file we just copied. And we can compile this. So there's no error, so we get this object file. Now let's link all this together and run it. Might as well take MLP. We need MLP and the minimax. Okay, so we get this executable. So now let's execute it. So as to train the MLP, it will take a while. So it has finished the training and begins to play. So the AI moves first. AI plays 0. This is from the MLP, and this is from minimax. Okay, the one within the parentheses is from minimax. So it marks at this position 0. Okay. And suppose we play say 4. Okay, so you can see that the MLP plays at 1, and the same as what minimax returns. Okay, so it puts an X here. So suppose we play 2. And AI plays 6. Okay, this X. Okay, so this is from MLP and this is from minimax. And suppose we play 3. Okay, so X is at X plays at 5. Okay, from the MLP. This is from the minimax. The same. Suppose we put F8 here. Okay. So the AI plays 7. Okay, this position. So the result returned by the MLP is the same as that from minimax. So the training was successful. Now the program has also saved the weights of the MLP into this test file, techweights.txt. Now we can take a look at its values. Okay. So these are the weights that have been saved. Okay. So next time when we use the MLP, we just need to read the weights back into the weights array. So we don't need to train again. Okay. So these are the weights saved. Lastly, we discuss using a GUI to play the tic-tac-toe game. We'll use the trained multilayer perceptron for the AI moves. We do not need to use the minimax anymore. So as before, player as MT, X, and O as elements, and AI is X, the opponent is O, the board is the tic-tac-toe board. And we define some Boolean variables. And this D is the joint distance between the lines of the tic-tac-toe board. Okay. Who won here, we determine whether the game is over. If it is -1, the game is not over. If it is 0, then it means X wins. It's 1. O wins, and 2 means a draw. Okay. So we create an MLP object. Okay. So we set the board is to reset the board. Now display message is to display a string at the location specified by X and Y. Okay, with this font. Okay. So we can specify the location using this command raster post to F, okay, XY. And now this is a C++ statement. It means look for each character of the string, okay? And then we use got bitmap to draw the character with the font. So this basically is to display a message, okay, specified by this string. Print board is to print the board, the tic-tac-toe board. It's straightforward. So these are the centers, okay, of the different squares, of the 9 squares, okay, specified by CXCY. And so if it is not empty, that means it is either X or O. So we draw it at the appropriate position, okay, with the display message. For X, we display it with red color, and for O, we display it with the green color. So if Q1 is larger than or equal to 0, that means the game is over. And we define the strings to be this, and then display the appropriate string. Okay. If Q1 is 0, then AI has 1 is displayed. If it is 1, then you have 1 is displayed. And if it is 2, it was a draw, is displayed. And here we define the graphics. Okay. Well, it's a very simple OpenGL program. Okay. So the screen width is 500, screen height is 500. Okay. And we define the world coordinates. For x is negative 10 to 10. Okay. Y is also negative 10 to 10. Okay. And we will draw the lines with black color. Okay. And here, MLP ways is to read the ways from this file into the ways array for the MLP. 9 is to draw a line. The display at the beginning is to draw the tic-tac-toe board. 2 horizontal lines, 2 vertical lines. Is winning tells who is winning. Whether the player here is winning or has won. Empty cell is to tell whether there's any more empty space. Okay, if yes, it returns true. Otherwise, it returns false. Board to inputs is to convert the inputs from the board, okay, to the array inputs, okay, as we discussed earlier. Okay, so this board configuration is converted to this inputs array. Okay. And out to move is to find a exact move from this out array. Check status will tell us who is winning, whether it is AI or the opponent, okay, or is a draw. If it's not done yet, it's -1. So this is the AI move. First, it has to check whether the game is finished using check status. If it's done, then the game is over, so it returns. Okay. Otherwise, it declares these variables and convert the board to inputs array and use the trained MLP to find out the outputs, the output array. Okay. So we use the forward member function and then use out to move to convert to move. So we put that location to be AI. Okay, is X here. Okay. And so play, the function will set the play emotion. And we let the AI go first. And to make it simple, AI will put the move at location 0. Okay. So that we mark the board with 0 to be AI, that's X, and then print the board. And now, after that is the opponent's move, so is set to true. Okay. And the other keyboard functions to press P, then we start to play, and R is to reset the board. Get location is to convert the coordinates to the board location. Okay, so board location is from 0 to 8. Okay. So depending on which point we click, and then we know where we want to put the symbol. So there's the mouse. Okay, when we click the mouse, if it is opponent's move, then we have to mark the location with O. Okay. If it is not the opponent's move, then it returns. Okay. And say in this function mouse, this will return the screen coordinates mx, my. Okay. So we have to convert to world coordinates using this formula. Oh, by the way, in OpenGL, say the top of the screen, left top corner is 0, 0. So that's why we need to do screen height minus y, my. M represents mouse. So if game 1 is more than 0, that means the game is not done. Then we get the location from the coordinates, and if the location is empty, then we set that location to be the opponent. Okay, there's O, and then next turn is AI move. So we set up move to false and print the board. Okay, so next time is AI move. So we get the move from the trained MLP. And again, check the status, and then print the board, and set the up move to be true again. So again, you will be waiting for a click. Okay. So this is the initialization of the graphics routine. Okay, standard. Okay, so that's the main. It calls this graphics. Okay, and of course you can always improve upon this program. So you can, for example, create the MLP here and pass in the object to other functions. Okay. So here we just make things simple and easy to read. Now let's copy this file and paste it into a test tick mlpg.cpp. G means graphics. Okay, and we save it. So this is the file we just copied. And we can compile it, G++ minus C. So there's no error, and this object file is created. Now we can link this together to get an executable. We need the MLP.o, also the graphics library, OpenGL, and the utility. So no error. So this is created. Take ways are the ways that we created using the training program, and now we don't need the minimax anymore. So we just execute this and press P to play. Click here and click here. So AI plays here. So click here. So it was a draw. Now let's we set it. Press R. Okay, and play. And suppose we click here, okay, and then here, and here. So AI has one. Now we set it, and suppose we play again, and we play here, okay, and here. So now we can win. So the MLP does not make the optimal move. Okay, so and we could win. Okay, so that means it's not perfect, and you could try other configurations to improve it. For example, you can try M1 to be 20. That means the number of neurons in the hidden layer is 20. I've run the program with M1 equals 20 and saved the ways in this file t20.txt. Let's take a look. add the ways. Okay, so they are essentially different from the other ways. Now let's copy this to take ways, and we need to recompile. Oh, we need to change MLP.h. We need to change this to 20. Okay. And recompile MLP.cpp, and maybe the main program also. Okay. And now let's we link them together. Okay. And now let's execute this. Okay. So P for play, and suppose I click here again. So now the AI plays here, and so we have to play here. Okay. And then we click here. Okay. So AI has fun. Okay. In this case, now let's try another case. Reset. Okay. P. Okay. Here. 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 See, it was a draw. So here, that when M1 equals 20, the AI works better. So you can try different configurations and see how they work. So this wraps up our discussion on this topic. Thank you for watching, and I will see you in the next video.